Thank you very much for the invitation and the opportunity to be here and speak about this work, which is a collaboration with Emmanuel Rodriguez Cirone from the University of Buenos Aires. I'm going to speak about the homotopy structuralizing KK theory. First of all, I would like to mention one colleague and a professor of mine who was Fernando Abadí. He made a lot of contribution in operator algebras, in particular Fell bundles, and sadly he passed away 2 weeks ago. I would like to speak in his memory. Then let's go. First of all, I'm going to recall some things about algebraic KK theory. I'm going to mention a result that we have in collaboration with Emmanuel about a relation with the KH isomorphism conjecture. And then I'm going to speak about homotopy structures in algebraic KK theory, in the sense of things that they are mentioned last week. Then what is algebraic KK theory? It's a theory which was introduced by Willy Cortiñas and Andreas Thom in order to show that some methods in operator algebras, in K-theory of operator algebras, can be applied in a completely algebraic setting. Then I'm going to work in the category of associative algebras over a commutative ring L with or without unit. Then last week, we had an introduction of Kasparov KK theory. I'm going to recall some part of the theory. I'm going to recall KK theory in terms of universal properties that this theory satisfies, not through the modules. Then what is Kasparov KK theory? It's a bivariant K theory on the category of separable sister algebras. Then for two separable sister algebras, it is define a group KK-AV, and this group form a category which is called KK. The morphisms in this category are the groups KK-AV. Then we have a functor from the category of sister algebras to this new category whose objects are the same and the morphisms are the elements of the groups. Then algebraic KK theory is a bivariant K theory on the category of algebras. Then we also have a category KK, little KK, associated that for if we have two algebras, we have a group KK-AV, and these groups are the morphisms of this new category. Then, as we saw last week, KK in the Kasparov sense is a triangulated category. In this case, also we have a triangulated category structure. And we saw also that this functor is stable with respect with compact operators. That means that if we have a sister algebra A and we take the stabilized sister algebra A that is tensoring with the compact operators, then these two sister algebras are identified in this category. In the algebraic setting, what we have is stability with respect to matrices. Then if we have this matrix with infinity index, which are the colimit of the matrices of size n times n, then these two algebras here are identified. Then we also have homotopy invariance. Here, if we have two sister homomorphism between sister algebras, star homomorphism between sister algebras, we say that they are homotopic if there is a map H here, such that if we evaluate, this is the continuous map from the interval to B. If we evaluate in 0, we obtain F. If we evaluate in 1, we obtain G. And the factor K is a homotopy invariant if each time that we have two homotopic functions, they are identified here. Or in the same way, we can say that these two algebras are identified in this category. In algebraic setting, what we don't have continuous map, but we have polynomials. And we say that two morphism between rings, between algebras are homotopic in elementary sense. If there exists a ring map here, homomorphism, such that if we evaluate in 0 or in 1, we obtain these two maps. This relation is not transitive, then we have to force transitivity in some way. That brings some technical issues. But the homotopy invariance identify these two algebras in this category. Okay. Then in this side we have split exactness, and in the side we have some excision properties. And the base ring, the algebras are algebras over the base ring. And I don't know if this was the question. The ring is a commutative ring with unit, the base ring.
Perhaps they meant that you never mentioned the base ring.
The base ring, I never mentioned the base ring.
Yeah, the little L.
Yeah, it's here. Little L is in Kasparov KK theory. If we put the complex numbers in the first input, we recover the topological K theory of the sister algebra A. Then here, if we put the base ring in the first input, we obtain the homotopy K theory of A defined by this. Okay. Then this algebraic KK theory has a equivariant version as in Kasparov KK theory. Then if we have a group, all the groups which appear here is without topology, then discrete group, a group without topology. Then we take the category of algebras with an action of G. Then we also can define groups associated to this pair of G algebras. And we obtain a new category, little KK+H, which is also triangulated. There is some matrix stabilization, and here we identify every algebra with its matrices with index in N and index in G. Here G acts on G and on A also in both things. Then we identify these two G algebras. As in Kasparov KK theory, identify these two sister algebras. The theory is also polynomial invariant. We have excisions, and this theory is universal. This functor is universal for these properties. Then, in this case, for example, we have an algebraic version of Green-Yell theorem. Then, if we take a finite group such that the order is invertible in the base ring, then we obtain the homotopy K theory of the cross product of G with A. Yeah. I don't know if there is some questions about the base ring is here now. It's appeared. Okay, let me speak a little about the KH isomorphism conjecture, because in the Kasparov KK theory, there is a formulation of the bound conjecture with coefficients using equivariant Kasparov KK theory. Then our question is if we can write, for example, the assembly map of the KH isomorphism conjecture using algebraic KK theory, equivariant one. Then I'm going to tell our previous results as a motivation of the talk. Then the assembly map of the bound conjecture can be stated in using two things. One approach is using the Davis-Luke assembly map. Then if you have a discrete group and a separable G-sister algebra, then we can consider the spectrum associated to the topological K theory. And this spectrum is used in order to construct an equivariant homology theory with coefficients in this spectrum. And if we apply this equivariant homology that is constructed by Davis and Luke to this map, this is the proper classifying space. Last week was also denoted by AG with some underline. If we apply this equivariant homology to this map, we obtain the assembly map. I write it that. But last week, we saw another way to express the assembly map of the bound conjecture, which is using the descent map and this idempotent element associated to every G compact X, which is a proper G space. Then if we take the colimit of over X as subset of this classifying space, we obtain the assembly map of the bound conjecture with coefficients. With coefficient because we have a sister algebra B here last week, where without the full the bound conjecture without coefficient is when here there is the complex numbers. Then these two assembly map were identified by Julian Kranz and also by Bunke, Engel, and Dahl using different techniques. Then we want to have some similar picture of this in the algebraic KK theory. We cannot express assembly map of a conjecture here in this way, because this construction has some difficulties. But then we don't have an assembly map with the left-hand side as an algebraic equivariant KK theory. But what we have done is to express the left-hand side of the assembly map of the KH isomorphic conjecture as a equivariant KK groups, the equivariant KK groups. Then the isomorphic conjecture associated to KH is also using Davis look approach. Then we have this, there is a spectrum, a phantom from the orbit category to the spectra associated to KH. And then the equivariant homology theory is constructed. And then we apply the projection to this equivariant homology, and we obtain the assembly map of this conjecture. Then we have done is to express this part in terms of equivariant KK. Oops. We don't have an assembly map with a domain expressed as equivariant algebraic KK groups, but we express the domain of this assembly map as an colimit of equivariant algebraic KK groups. My idea is not to give details about the proof, but these techniques are very different from the techniques used in the bound-cone conjecture setting, because we use a concrete spectrum representing KK, algebraic KK. Then a question is still open is, okay, can we define an assembly map for the KH isomorphic conjecture using KKG? We express this group as a KKG, but not the assembly map. Then the ideas used in Kasparov KK theory, identifying different assembly maps, was using Meyer-Nest approach that was mentioned also last week in the talk of Christian Fock. And the strategy to identify the assembly map expressing using Davis look approach and expressing descent map is replace them. Then the techniques used in the bound-cone conjectures context are different. Then the idea of Julian Krantz is to is use Meyer-Nest approach, and if you have a sister algebra B, you replace by a B tilde who lives in the C compact the CI part of the induced. This is a algebra which is compactly induced. Then Then here at this level, this morphism, the assembly map, in the context of Davis look and the also in the other context are isomorphic, then these two maps are identified. And then the other work identify these two assembly map using a stable infinity category structure on KKG, and also they use some coarse geometry techniques. Then that's why we ended asking if we can do something similar in algebraic KK theory. Then that's what I'm going to talk about. Then let me just clarify the structure of the triangulate category KK. I'm going to recall the triangles there. Then if we have an algebra A, we take the path algebra, which are the polynomial who vanishes at 0, and loop algebra, which also vanish at 0 and in 1. And then these two algebras fit into extension, loop extension. This is an extension, it's exact. This is a, then if we evaluate in 1, and we take the kernel, and we take, or the inclusion. We don't have kernels, but the composition is 0. And then this loop algebra is the suspension of the triangulate category KK. That means that this loop algebra induce a map at the level of the category KK, and this map is an equivalence. Then, in order to show you the triangles, the distinguished triangles, if we have an algebra homomorphism, and we take here, and we take the loop algebra here, then we take the pullback here, then a triangle is distinguished if it's isomorphic to one of these 4 in KK. Then the question is, can we find a stable category of fibrant objects such that the homotopy category is KK as a triangulate category? Or can we find a stable infinity category C such that the homotopy category is KK? These are the questions. And let's recall what is an infinity category. We saw some different statement about the stability of infinity category. I'm going to use this one. A stable infinity category is a pointed infinity category that admits limits and such that the loop functor is an equivalence. Then I'm going to tell you how to construct it. This last part I'm not going to mention, but it's the way to prove that the loop functor, that is a construction that also was recalled last week, is an equivalence, is because the loop functor coincides with the looping functor, which we know that is a KK equivalence. Then this part is almost done. Then we have here, in order to construct a stable infinity category, 2 options. One option is follow the work of Marcus Land and Thomas Nicolaus, and take the category Ag as an infinity category via the nerve of the category, and localize by the KK equivalences. An algebra morphism is a KK equivalence if in KK is an isomorphism. Then this is the first option, and the second option is to follow the work of Ulrich Bunke and force the property one by one. Then the other option is localize first for the polynomial homotopy equivalence in a way to force homotopy invariance. Then we localize by the set of upper corner inclusions and force the matrix stability, and then finally we can localize by these classifying maps in order to force excision. Then okay. The first option is done. The second option is, it has some troubles, some problems that I'm going to tell in the rest of the talk. Well, I don't know. Well, I don't know if the chat is. Then, in order to make the Dwyer-Kahn localization of KK equivalence, we need to revisit universal properties. Then we have that the functor, this functor is universal of with respect to the properties in the world of triangulated categories, but we need to move on. Then we have this new version of universal properties in the world of the categories with finite products, and the functor preserve these finite products. Then what we have is that the functor from the category of algebras to KK is initial in the category of those functors, such that has finite products, F preserve finite products, and all of the maps in these sets are invertible, are isomorphism in C. In this, then this theorem allows us to write KK as the localization of the category of algebras with respect to KK equivalence. Then then we can take we can take the algebra, the category of algebra, the category of algebra, and localize through KK equivalences via the Dwyer-Kahn localization. And then what we have is, by universal properties, we have a functor from this new category, KK infinity to KK. And we want that the homotopy of this functor is a equivalence as a triangulated categories. Then we have constructed an infinity category, but we need to know if there is a stable. We need to control what happened with finite limits. Then the way to control that is localize category of vibrant objects. Then we use results given by Szysinski in the infinity categories wall. Then what we need to understand if the category of algebras has a category of vibrant object structure in order to know if we have finite limits or not. Then a category of vibrant object structure on a category C consists in a terminal object and fibrations and weak equivalences, such that they satisfy some properties. We need to fibration be closed under composition. Isomorphism of the category are are fibrations, and the pullbacks of a fibration is a fibration. We need the elements. The object are fibrant. That means that this map is a fibration. Isomorphism here are weak equivalence. We have 2 of 3 property. And we also need that the pullback of a trivial fibration is a trivial fibration. And this is in red because I'm going to show you that sometimes in some structure that is satisfied, and in other structure we have problems. Then in the how following what happened in the category of C-star algebras, then in the work of Uye, there is 2 examples of these categories of vibrant object structure. Then they consider in the category of C-star algebras enriched over top, taking in this set the compact open topology. The fibration are called Shoshev fibration, which induce a self fibration here. And we are going to consider KK equivalence. That means that we have a morphism in a star morphism between C-star algebras is a KK equivalence if this is an isomorphism. And one thing that is satisfied in the context is not a definition, because we have we know what is a homotopy equivalence, but something that it satisfies is that this map is a homotopy equivalence if the induced map is a weak equivalence for every C-star algebra T. Then the theorems here say that if we take the category of separable C-star algebras, the fibrations, the Joseph fibration, and the homotopy equivalences, we obtain a category of fibrant objects such that the homotopy category of this structure is the homotopy, the strong homotopy equivalences in C-star algebras. And if you take KK equivalences instead of homotopy equivalences, what we obtain is the category KK. Then the question is, what happened in our context, algebraic context? Then what happened if we take the polynomial homotopy equivalence for one side and little kk equivalence to another side? Then what we have is that if we take the category of associative algebras with the fibrations such that are surjective morphisms which have a linear section and KK equivalences, we have a category of fibrant object. Here, all of the axioms that I show you in this structure are straightforward, but the only part is, the tricky part is to prove that the pullback of a trivial fibration is a trivial fibration. We have to use a version of Mayer-Vittori sequence in little kk. Then as we define the infinity category as the localization of a category of fibrant object, we know that there exist finite limits. We have finite products and pullbacks. And the functor induced is an equivalence of triangulated categories. And this is our main theorem following the work of Marcus Land and Thomas Nicolaus. What happened if we replace KK equivalences by polynomial homotopy equivalences? Well, what we have is we don't have a category of fibrant object. Moreover, if we replace this set of fibrations by another one, for example, the map such that induce a configuration. If we replace by any set of fibration, we also don't have a category of fibrant object. Then let me show why we don't have a category of fibrant object. And we have the paths. Let's consider A. A can be the base ring here. Then we have the polynomials such that vanish at 0. The pair of polynomials, this is the pair of polynomials such the first one vanish at 0, and if we evaluate this in 1, coincides with this one in 0. And we have the loop algebras, this one which vanishes in 0 and in 1, and this such is the same like this, that vanishes also in 1. Then in algebraic homotopies, we have to deal with a sequence, an int algebra. Then this is the first two part of the sequence. Then these algebras can be expressed in then we have pullbacks here. Here we have this algebra. We evaluate in 1. We have a fibration because it's surjective, and we have a splitting. Then we have here we have a pullback, and we also have a pullback here. And we have these two algebras are contractibles in the algebraic context as a homotopy algebra. And then we have this map. We have a map of pullback diagrams. And if this structure is a category of fibrant objects, then by the co-gluing lemma, this has to be a homotopy equivalent, because we have a morphism between pullbacks, then this has to be an homotopy equivalence. But we prove that this is not an homotopy equivalence. The proof is here. Then this map, I would like to stress that this map, if we see in continuous map, this is an equivalence, it's an homotopy equivalence. But let me show you why here is not an homotopy equivalence. Then suppose that A is a domain such that the homotopy K theory is not vanished. Then if we suppose that beta is a polynomial homotopy equivalence, then the class is invertible in this category, in the category of homotopy class algebras, morphisms. Then we have an inverse. And in particular, this composition is the identity here. And what we have is that if we multiply these two things, because the alpha is an algebra homomorphism, we take that this is 0. Then as the polynomial over here is a domain, we have, if this is 0, it should be, this should be 0, or this should be 0. I'm going to suppose that this is 0, the other case is similar. Then we obtain that if we compose alpha with beta, we obtain the zeromorphism. He's the making the count. Then if alpha composing beta is the zeromorphism, we obtain that the identity of the map is the 0. Then we have this is a 0 map in the category of algebras. But this cannot happen because we are assuming that the homotopy K theory of L is not 0. That's, for example, if L are the integer numbers. So an example. Then beta is not a homotopy equivalence here. But it's a KK equivalence. It's using escission, and this is a KK equivalence. And then in order to finish, and I'm going to resume the steps that we have done. Then the category of system algebras which assert vibration and KK equivalence is a category fibrant object in the algebraic setting. We have the surjective morphisms with algebraic KK equivalence is a category of fibrant object. Then the universal properties revisited say that the functor, this functor is a localization along the KK equivalences as in the Kasparov KK theory. Then we obtain a stable infinity category such that the homotopy category is KK, following the work of Marcus Land and Thomas Nicolaus. And we also have an equivariant version of that, following the work of Ulrich-Bunge, Engel, and Land, which use also the Land-Nicolaus program in the equivariant case. Then that's what we have. What happened with the option 2? Okay, we prove that this is not a category of fibrant object. Pardon, sorry. This is not a category of fibrant object, but in the case of Kasparov, in the case of sister algebras, here we don't have KK. In the case of sister algebras, we have this a category of fibrant object. This structure is also interesting because the don't come of a model category. It's not the fibrant part of a model category. It's proof in the same work. It's interesting. But in the algebraic case, we don't have the structure. And what does it mean? That means that we cannot follow the step suggested by Ulrich-Bunge, because he used that this infinity category has finite limit using the structure of category of fibrant object here. But we don't have it. In fact, what we have is that these two Milnor squares, which are we have a surjection here with splitting. these two squares do not give pullback simultaneously in this category because of the beta, because we proved that beta is not an equivalent. But we have some results, positive results. If the category alg can be enriched over Kan complexes, and then we can take the coherent nerve of this category, and this is the coherent nerve of the enriched category with respect to Kan complexes. Then this map is the dual Kan localization of the category alg view as an infinity category through the nerve with respect to polynomial equivalence. This is there is a result in the work of Uli, which stayed the same for cis algebras. Okay, I think I finish here. There is some references.
Your last slide is, thank you. Yeah.
And thank you for listening.
Yeah, let's thank the speaker. Now, are there any questions? Okay, Uli.
Okay, two. So one thing, I mean, so your argument shows that, I mean, you don't have the structure of the vibration category, but it doesn't disprove the statement that the localization of the algebras at homotopy equivalences is left exact somehow. Yeah, I mean, you only say that a certain pullbacks in algebras do not become pullbacks in the,
Yeah.
but so this is the first thing. So I mean, you say you have this via Kan localization if you do the fibrant, I mean, the Kan complex enrichment. So do you know whether this thing is left exact, or can you disprove left exactness at this level? And I mean, the other thing is just a remark. I mean, so somehow in your definition, you prefer in the polynomials evaluation at 0, yeah, in contrast to evaluation at 1. So it's not symmetric. Yeah, so somehow maybe that is the reason that you have these problems with the evaluations, yeah, because your path object is somehow, it's not symmetric, yeah. If you evaluate at 0 and at 1, it's different things. So, but anyway, so somehow I'm more interested in the first question. So is it left exact one?
Yeah. Well, what we have is that this we want to this square is a pullback, and it's not because of what we prove. Maybe I don't know.
I mean, your path object is not symmetric. You cannot reverse path. Then you don't get the path object anymore. That's why I asked some of the first question. I was confused about what you call path object. So for me, the path object would be just polynomial algebra, which is not constructible, but it's a thing which is a path. Yeah, but somehow I mean, your path object is a sort of cone. Of course, you have another cone. I understand, but I mean, this thing is not symmetric. Yeah, if you're in I. So if you evaluate at 0 or 1. So I don't know whether there's a more symmetric definition. Somehow that's probably the reason why this doesn't work.
It's not symmetric, maybe it's equivalent because you can invert, you can, yeah. Yeah, I don't know, but it's I don't know if we have some more symmetric way. That's a nice question. Maybe Fema is here.
I have nothing to say about this. I don't know. I get the point, but I haven't thought about this.
Yeah, but I think that is a good, a really nice question to think about, or not.
Any other questions?
I would like to ask a question again that I asked the chat very much in the beginning. So there is the category of non-commutative motives, which is sort of the universal localizing invariant. I mean, it maps from stable infinity categories to spectra, but you can pre-compose it with the category from algebras to stable infinity categories. So this is obviously not a homotopy invariant functor because of little terms and things appearing, but you can force it to be homotopy invariant by doing a further localization of the category of non-commutative motives. And one could wonder if this is the same, if this localization would give the same thing as your KK, or as the term continuous KK. Is anything about this known?
I don't know about the non-commutative motives stuff there. I don't know.
There is a paper of Tawada showing that certain properties. I mean, I have a couple of papers concerning Levitt-Pass algebras in KK, and Gonzalo did show that the same holds in the A1 localization of his non-commutative motives. But I mean, I don't think I think he stopped short of actually showing that that KK is the A1 localization, but I wouldn't be at all surprised. But there is also, I mean, the setup in Gonzalo's work are DG categories, and we only have algebras. So should promote KK to DG categories first in order to be able to even state this.
Yeah, some people say that.
Somehow we have. Sorry, please continue.
No. We have simplicial algebras, not DG structures. Then I would like to understand. It is an interesting question to compare both settings, I think, but it is not clear for me because it's different context, as Willy said.
Okay, thanks. Yeah.
Yes. Let's stop the recording now.